Yeah, it's recording. Say a couple of lines of introduction for yourself.
So we're good to go?
Yeah.
All right. Well, thank you all for coming out. My name's James Nagel. I got my PhD here in 2011. Just jump ahead. I give this lecture every year for Dr. Manan. It was my PhD subject was light trapping in thin film silicon solar cells. And so he likes to invite me in to talk a little bit about that subject. And then immediately after that, I went on to work for a startup company called Terahertz Device Corporation, where I did light extraction. So, fun fact, those two ideas of light trapping and light extraction, all the physics for that is basically the same. It's just kind of one's the backwards inverse from the other. So that makes two nice lectures that go back to back. And this should be a fun and exciting adventure. So what's light trapping and why is this important? What do we care about it? The basic idea of light trapping is you start with a thing, okay? Some object in space, and you're just shining light on it from some direction here. And naturally, some of that light will scatter off, some will maybe miss it entirely, some might bounce around and eventually leak out the other side, and some tiny little bit will even get absorbed in there at some point. So that idea of light trapping is exactly what it sounds like. You shine light on a thing, and we want to measure or quantify the energy absorbed within it, and then normalize it by the total energy that's actually hitting it. So obviously, we don't care about light that maybe is missing the thing entirely. And that's a surprisingly rich and deep subject, full of lots of magical twists and turns. So what are some applications we might expect for the idea of light trapping? Why would we care about it? What good is it to want to trap light inside things? So an obvious application might be, stealth bombers and blowing things up. Because when you go flying over bad guy territory and they're pinging radar everywhere, it's nice to not get noticed. So one of the big areas of research in stealth is that magical black paint that absorbs all the radar energy that goes into it rather than scatter it back towards the center. You also have, of course, solar cells, which is what we're going to focus on today because this is optics for energy, and nothing creates energy quite like solar panels. Another fun application might be like an anechoic chamber here. So I think this is actually a picture here at the U, if I'm not mistaken. No, actually, that might be. That looks different. Yeah, might have been. I don't know if I stole this online or dug it up from another chamber it was at years and years ago. But obviously, you're in this closed room, you're shining radio waves on some little object under test here, and some of that energy might scatter off it and bounce off the walls or create echoes, which can disrupt your measurement. So this magic foam padding here on the walls here is designed to absorb all the energy that hits them and prevent echoes. So anechoic, not echoing the chamber. So optics for energy, let's talk about solar cells in particular. So this is a fun little graphic I always like to start with to kick off the discussion. We all know the demand for energy in the world is growing. A lot of those poorer countries are industrializing and using more energy. The United States is constantly growing at a rate of good 2 to 3% per year, and the demand for energy tends to grow with that. And fossil fuels aren't going to last forever, and then there's that pesky greenhouse thing that everyone's talking about. So sooner or later, we're going to have to find other sources of energy and start exploiting it. So this is a really cool graphic from NREL. We're going to cite them a lot. It's the National Renewable Energy Laboratory. And it just kind of shows the solar insolence, I think is the word, across the United States. So you see down here in Arizona and New Mexico, where it's a big hot desert, there's tons and tons of sunlight. And up here, say in Maine, it's a little greener. And of course, Alaska is cold and frigid. So there's not a whole lot of sunlight there. The one fun fact people often like to cite when they're talking about solar energy is the fact that if you took all the solar energy that hit the Earth in 1 hour, you could, in principle, use that to supply the entire world energy demand for 1 year. So solar power is very plentiful in that regard, and the sun isn't going to dry up anytime soon. Last I checked, there's a couple billion years left before it develops us and kills us all. So that's not going to run out in any particular time frame we care about, the way And this is in contrast with like fossil fuels, which really at the rate we're going may only last another 100, 200 years tops. So this is a nice long-term solution to a lot of our energy problems if we can somehow harness all of that sunlight. So this little graphic here shows kind of a nice big solar array out in some desert somewhere. And I like to point this out to say the technology for this technically exists. Like there it is. Sorry, do you have a question before I go? Or are you just scratching your head? So the technology exists here, right? And in principle, like if we could just, like see that little laser pointer right there? Like if you were to build a solar array that's to that scale of that laser pointer, which would be like 50 square miles, say, all the energy on that little dot would in principle supply all the energy to the United States. So the big question is, why aren't we just flooding the Arizona desert with solar cells and supplying all our energy from now until eternity? Go, someone answer that. Spitball it.
Well, rare earth metals are used in most of the solar panels today.
Okay.
So there's a
rare earth metals?
Yeah, rare earth metals.
Are they really?
Are they what?
Are they really?
Rare?
Yeah.
Well, it depends on, I don't know. The older solar panels are definitely rare. I don't know if the newer ones are.
We'll talk a little bit about newer solar panels. That's not really a thing in newer stuff.
Storage?
Storage is a big problem, right?
Okay.
Because the sun isn't shining all day. This is only I think this is a peak value that they see. Obviously at nighttime you get nothing, so you'd have to store it in some capacity, and that's not a trivial problem. There's also the transmission problem. Like, how is someone up here in, say, Alaska going to benefit from a solar array here in New Mexico without some 9,000-mile long transmission line going up through Canada, right? So that's a big problem too. So it may have some local advantages to it, but in the big scheme of things, there's a lot of obvious technical challenges involved. Another one that tends to get overlooked a bit is cost. So 30, 40 years ago, the cost of a big giant solar panel would have been very expensive. And the way this is normally broken down, you notice the units here are dollars per watt. So if I want to build, say, a big megawatt facility of solar panels, with the sun shining on it and generating 1 megawatt, how many dollars do I have to invest in this thing to create that facility? And you can see back in 1991-ish, it would have been $10 per watt. So a 1 megawatt facility would have hypothetically cost you $10 million to create. Compared to something like coal or natural gas, that's actually very expensive. So for a long time, there was this big push by industry to bring the cost of solar cells down to the scale of $1 per watt, which was kind of regarded as the break-even point where solar energy suddenly becomes cost competitive with fossil fuels or coal and that sort of thing. And the word they used was cost parity, I guess. So fun fact, right around 2015, 2016, 17, we started breaking that threshold, which is really, really cool. And for that reason, you'll notice the cumulative global shipments in terms of megawatts has been going up as a function of time. So you see 1976, 81, 91, 2001, 8, 2017, and we're upwards of somewhere around 500,000 megawatts of capacity in 2017. And on top of all that manufacturing capacity, you get huge economy of scales, and which is why you can see this giant drop as well. It's kind of like this Moore's Law sort of thing with the solar cells. So that's really cool. And sooner or later, they're just going to be so cheap that we don't even need some giant federal initiative to install solar panels everywhere. People will just do it naturally of their own accord because it will just make pure economic sense to do so. So that's been the big goal with the Department of Energy and the National Renewable Energy Laboratories, is not to try and force the issue, but just to put so much research into manufacturing and cheapening of this stuff that we don't even have to lobby Congress for it. It'll just happen entirely on its own. So let's break down some of the basic physics of a solar cell. So here's a nice, simplified, idealized graphic of what a solar cell might look like. So you have some layer of a semiconductor material, and you dope it p-type and n-type to create a p-n junction. Photons from on high come swooping in and penetrate inside this solar cell. And by some fluke, every now and then, one of them will bash into an electron and excite it to an elevated state to create an electron-hole pair. Then, of course, the electron will just meander about on this Brownian walk and eventually get captured up here in the top contact. And then the hole may wander around to the bottom contact. And at that point, you can do meaningful work with it. So that's just it's a little oversimplified, but it's good enough to kind of get the ball rolling. So the first step is, I guess you could say, what do you make this thing out of? So you're talking about rare earth metals and that sort of thing. That's not really what you see in modern solar cells. I think if you take Mike Scarpola's photovoltaics class, you'll even make your own solar cells in a lab. I should have brought the little module in. You can do them on little wafers. They're just silicon and aluminum and PN doping is all you need to make your own solar cell. So fun plug there if that sounds interesting. So right here, we have a layer of silicon, PN junction, kind of drawn pseudo to scale here. You might see a little bit of silver up here in the contacts. I don't know if that's really necessary. This diagram says, was that palladium, PD, titanium? I don't think you really need all that stuff. Titanium's pretty abundant though. But the bulk of it here is silicon. So why silicon? Why not gallium arsenide or gallium antimonide or cadmium telluride? Those are all things that people have used to make things like solar cells. So the first reason, which is kind of what you alluded to, is the abundance of it. The total global manufacturing of silicon is just hugely abundant. We're not really going to run out of this stuff anytime soon. There's just more than enough of the raw atoms of silicon in the Earth's crust to supply a lot of our world's energy demand. And that turns out to be a very important thing because back in, I think, like 2012, 2013, that general time frame, there was a company called First Solar who came out with like the world record for just a cheap, efficient solar cell. But they made it out of cadmium telluride instead of silicon, which was really neat in the fact that it was cheap, but cadmium and tellurium aren't exactly the most abundant metals in the world, which means there was a very sort of strict upper limit to how much these things could be manufactured every year. So that simple material abundance is a very, very big deal in terms of manufacturing capacity for satisfying all of our global energy needs. Another key point is non-toxicity. So for example, imagine I've got a big solar cell and I run it up on my roof, and then 20 years later they start falling apart and I chuck it into the garbage. Eventually, a lot of this stuff is going to start ending up in landfills if you're not careful. So you have very aggressive recycling programs. So again, you think about cadmium telluride. Is that the kind of stuff you want to just start throwing into landfills where it will get into ground tables? Well, cadmium and tellurium aren't exactly the nicest metals for groundwater, and you get a lot of pollution issues with that. So again, silicon, however, isn't so bad. For example, if you were to reach out and grab a giant scoop of just dirt from outside, I believe the number is about 25% of just the raw atoms in your hand will be silicon of some kind. It's something like 1/4 of the Earth's crust is actually silicon or silicates. So since that's not really poisoning us at any particular moment, it's safe to say silicon is way less toxic than something like cadmium. Processing is important. It's fairly easy to make solar cells out of silicon. The band gap is another big deal. Fun fact, silicon, just by a wild fluke of nature, has just the right band gap to make surprisingly efficient solar cells in comparison to other materials. So that's an important step there. And then also by a wild coincidence, in the last 50 years, we've had this wonderful industry of computers and semiconductor manufacturers making laptops and desktop computers for us, who have all figured out how to process silicon on a huge scale. So it all just sort of happened to exist already when people started looking into make solar cells. So that's another kind of just institutional inertia of why silicon is kind of the dominant material of choice for a solar cell today. So let's talk about sunlight a bit. So this is a fun graphic too. It helps to really understand the sun before you start engineering a device designed to capture sunlight. So for that, the National Renewable Energy Laboratory, NREL, they put together what is called air mass solar spectral standards. So you start with this idea of an air mass zero spectrum, which is the black curve here. And this idea is you imagine yourself floating out in orbit far outside of Earth's atmosphere, and you just kind of point a photometer at the sun and do a spectral analysis on all the light coming in from the sun at kind of a mean Earth orbit. And this black line is roughly what you will see. It's not actually what you see because maybe the Earth's orbit is elliptical, so if you're a little closer, it might be a tad bigger, and if it's a little farther away, it'll be smaller, and depending on solar flares and sunspots or whatever, a lot of these garbled lines will jigger around. So what they do is they take all that data, they just kind of average it out over 1 year to give you this spectrum here. That's the idea. Also, a fun fact, this red curve here shows an ideal black body radiation spectrum, which kind of fits to it pretty well, and just so happens to coincide with roughly 5,800, 6,000 kelvins, give or take, depending on your mood and how nicely you think that curve is fitting. But that's a good way to determine how hot is the sun, really, at the surface. So it's about 6,000 kelvin, give or take, in case you're ever wondering that. So the idea now is you look at the units here, watts per square meter per nanometer. So it's not really a power density. It's a power density spectral density. So the idea is if you integrate over this entire curve, because all these photons are not at a single wavelength, they're different wavelengths. So the area under this curve would then give you units of watts per square meter, which then implies, say, a 1 square meter aperture pointed at the sun collecting photons. And if you measure all the power going through that, you would then get 1.366 kilowatts per square meter from the sun. So that's not bad, but the reality is going to be a little sadder if we start examining things. So the next step is to say, okay, we're not actually out in orbit per se. We're standing here on the surface of the Earth, and there is a giant layer of air above us that the light has to pass through before it can reach our little solar panels. So that is called an air mass 1.0. If you imagine yourself standing here at the equator and the sun is exactly overhead, there's one air mass of air, I guess, for the light to go through before it hits you. However, we in the United States are not really concerned with that because we're at this offset latitude, and it can vary a little depending if you're in Arizona or Maine or New Mexico or Alaska. So what they do then is they say, okay, imagine you're in the United States, and we're just going to kind of pluck some random location from the continental U.S. at random and look up at the sky and kind of average the intensity that we see throughout the year, throughout all the land. And so that red curve represents the average intensity that we would see. It's like the expected value of the solar insolence across the United States. So if you're in, say, New Mexico, you would actually see a lot more energy than this. And if you're up in Alaska or Maine, you would see a little less. But if you're kind of in, like, I don't know, Ohio somewhere, it's probably going to be about right. So you notice this also says air mass 1.5. That's because the sun is never really quite directly overhead. Because we're at the high latitude, the sun's sort of off to this angle most of the time. So you imagine there's 1.5 air masses of light that you have to go through. So that's why this red curve is a little less intense than the black curve. You notice all these little dips and valleys here from, like, this is probably carbon dioxide and water absorption and who knows what all this other stuff. If you're an expert in spectroscopy, you could probably identify all those little peaks. I'm not, but that's basically what's happening there. So again, you do the same thing where you integrate over this whole thing, and you get about 1 kilowatt per square meter, which I think is probably by design by NREL to give a nice round number. So this is often used as just kind of a standard measure of how much sunlight is the U.S. see, or U.S. experience, and so this is used to sort of calibrate all solar cells. So if you come out and manufacture a solar cell, you need some way to specify how good your solar cell is, because it may work better in Arizona than in New Mexico than in Maine. So what they do is they create these fancy, lamps that generate this exact solar spectrum, and then you calibrate them against that. So there's a nice standard of calibration by which all solar cells can be referenced against. So that's a fun little bit of photometry there. So now we want to talk a little about this idea of how do I quantify sort of the efficiency of a solar cell and ask ourselves how good can it really be. So the first thing that happens in a solar cell is it doesn't really capture energy per se, it really captures photons. So it's kind of a photon grabber. And in particular, there's this band gap in silicon right around 1120 nanometers. So you imagine, there's a photon of that wavelength would have some associated energy to it. And so all the photons to the left here have more than enough energy to get above the band gap, and all the photons here to the right have too little energy and cannot excite an electron hole pair. So for all practical purposes, all these photons here to the right of 1120 are useless to us in a silicon solar panel. So what we do is we convert our units from watts per square meter to photons per second per square meter instead. And we're going to capture just the photons, and we're going to throw away all these guys out here to create this little spectrum instead. So this now represents the usable spectrum of photons that are incident on a silicon solar cell in particular that are available for us to capture. So now if we integrate the area under this curve, we find that in principle, the best we could do is 811 watts per square meter using a silicon solar cell. Now, unfortunately, it's still not that great because what will happen is some photons will be greater in energy than the band gap. So what happens when you excite an electron-hole pair and the electron is way above the band gap level? Does anybody know? Have you talked about that at all?
Get a lot of heat, it excites up and it thermalizes
Yep,
back down.
it goes up and then it wobbles all the way back down to the band gap energy. So all that extra energy in the photons that were way in towards the blue spectrum, all you get is just the band gap energy, and anything more than that is just lost. So what you have to do then is you integrate and you only account the band gap energy and you throw away everything else. What you find is the total power you could possibly get out of a silicon solar cell is actually about 488 watts per square meter. So roughly, right there's a hard upper limit of about 48.8% efficiency on a silicon-based solar cell. And that's just the raw physics of how this thing works dictate that you cannot possibly ever do better than that. Unfortunately, it gets even worse than that because if you further apply some circuit theory and power delivery stuff and some thermodynamics, you lose a little bit more, and the true upper limit is actually more like 32% for a silicon solar cell, which isn't that bad. So there's 1 kilowatt per square meter hitting us, but in principle, we can only capture maybe about 320 of those watts using a silicon-based solar cell. So that's called the Shockley-Queisser limit, fun fact, and it's really kind of a hard physical upper limit to the best you can do with this sort of technology. Not without fundamentally just overhauling the basic physics of what you're doing. So that's going to be kind of a nice little reference for our discussion here. So what is the best you can actually do in practice? Because that's physics says you can only do about that good. People have tried very hard to get as close to that as they can. So this is a fun little graphic from 1999, where a bunch of scientists said, challenge accepted. We're going to see if we can get as close to that as we can. And they were able to achieve about 25%. And that was just pulling out all the stops, using the best silicon they could, using all these anti-reflective layers, minimizing the contacts and all that wonderful goodness. Notice the thickness here is 400 microns, which is actually kind of ridiculously thick for a solar cell. So 25% in the lab is basically what they got. I doubt anyone's done significantly better than this since 1999. I'd be surprised if the current world record is any more than 26 or 27%. But I would love to see what the present world record is. But every time I looked into this, all that I would see is like 25.2%, or and someone would come out with 25.5%. We win now. But nobody's really fundamentally breaking it. So that's in the laboratory. But what can you buy off the shelf? So this is a solar panel that I looked up on Amazon a couple years ago. So you just look up like high efficiency solar panel, and this is something that might typically come up. And you notice that it's got these little wafer modules that are all stuck together, and they're using really high purity crystalline silicon in those things probably. And they are coming out at 15.46% efficient. So just to give you a little idea of the really kind of the state of the art and the ability to capture energy with a solar cell. And this other value here, $1.8 per watt, is also an extremely important number because the lower that number gets, the more cost effective it becomes to install these things on your house or put them out in the desert. Part of the reason why these things are so expensive is you'll notice, again, these little modules are about 100 square centimeters, give or take. And that adds a lot of manufacturing costs because they all have to be kind of created individually and then assembled. And it's kind of a necessary step in manufacturing that gets in the way. So we'll see kind of in other variations how we can get around that to make these things very cheap. So let's talk about what are some reasons why we can't create the world's perfectest solar cell. So we're going to focus specifically on the problem of the light trap and really there's a lot of extra layers of issues that come up when you try and make a solar cell. For example, there's the recombination loss that happens in here, and then there's your power matching to your actual circuit, blah, blah, blah. But none of that matters if you can't at least get the photon captured inside your solar cell in the first place. So first things first, your light is coming in, again, from on high, and it encounters this dielectric barrier, and immediately some of that light's just going to bounce away. So we'll call that a reflection loss there. And then some will transmit through and maybe get caught. And of the light that does get through, sometimes it might just hit the bottom contact and bounce right on back out again. So there's an official word for that, so I call that like transmission loss or the back and forth reflective loss or something like that. The surface contacts up here are also a big problem. Ideally, you'd like to just have surface contacts covering the entire surface there, but then you block light from even getting inside the cell. So there's a big trade-off involved there in terms of I want lots of contacts here for the particles to meander up and get collected at my electrodes, but too many of them and I'm just blocking light again. So we try and minimize this as well. So step one, let's just do our best to minimize that. I think in practice you may only lose 1 or 2% on just the coverage of all the little surface there. In fact, we can look back here. So do I have a picture of a close-up maybe? Yeah, there you go. So you can see they're trying very hard. You have this main sort of contact here, and then all these little kind of strands here. So they're trying very hard to keep a nice uniform area of coverage without really blocking too much of the light. But even then, there's kind of a trade-off there. You necessarily have to lose a few percent of your efficiency just from that alone. Where are we at here? So step one, we'll try and minimize it. And that'll help a lot. Step two, let's put on an anti-reflective coating. So there's, I don't know, have you guys taken 3300? Who are electrical engineers in this class? So did you take 3300 yet? So you remember you did like the quarter wave transformer with a transmission line and that sort of thing? So that's basically what an anti-reflective coating does. It's really efficient at minimizing a lot of those reflections over a surprisingly large bandwidth. So that helps a lot with all that surface reflection. But we still have this problem where light will just kind of go through, hit the bottom, and then just fly on out again. So how do we mitigate that problem? Well, the simplest answer is make your solar cell really, really thick, right? Because it just follows kind of an exponential probability, and if you make it thick enough, it's bound to run into something sooner or later and get captured. However, you can't do that forever, right? So who can tell me, maybe just spitballing, why this might have some diminishing returns on it?
Electron hole pairs have too far to travel.
Yes. If you make them too big, they'll meander around and they recombine before they reach your electrodes. Another problem that's not quite so obvious is that this silicon stuff here, your raw wafer, costs money. And there's a fixed dollar value to just the atoms of silicon that have to go into this thing. And if you make it really, really thick, you're going to actually see that on the bottom line. So the price of silicon has actually come down a lot in the last several years, but it's still a fixed dollar value that you can't really push that either. So ideally, we'd like to make it really thick, but in practice, you lose a lot in terms of your economics and your efficiency for these two reasons. So we'd like to try and minimize this thickness if we can, while somehow still preserving all that light trapping. So let's quantify that some. So here's a fun little graph I just put together a long time ago. So you see it's crystalline silicon, gallium arsenide. This is the absorption length of the material as a function of the wavelength. So the absorption length is defined as how thick does this material have to be before you have a 1/E probability of capturing that photon, or I think probably is a better way, 1/E probability of, 1/E decay on the field amplitude is actually a better way to think of it. So that's the 63% decay length for an electric field vector there that goes through. And you can see how, as you approach the band gap for silicon, the absorption length kind of skyrockets off to infinity almost. And so you see here, maybe towards in the blues and the greens, your absorption length is barely even a micron or less. So you're actually capturing a lot of those short wavelengths very well, but you start going towards the red and near infrared, now you're at 10 microns or even 100 microns in thickness. So that's going to cause some problems for us. So thin film solar cells were all the rage back in 2011. So this is a fun little demo I did, where I just went again to Amazon and looked up thin film solar panels, and you see this kind of stuff. So you notice when they go thin, rather than being several hundred microns thick, they're only like 1 or 2 microns in thickness. You notice also they made it out of amorphous silicon, so they cut some corners on the quality of their silicon. And the dollars per watt is significantly less, $1.2 per watt, as opposed to the 1.8. However, you also notice they took a huge hit on their efficiency. So overall, it's a lot cheaper, but we lost a lot of that efficiency. So in principle, this number could be as high as 32, but we're way, way below that. And we'd like to figure out ways to keep it as high as we can. So here's a nice little graphic showing just sort of the electric field decay. So here's 500 nanometers going through a 2 micron thick idealized model of a solar cell. You can see at the shorter wavelengths, 2 microns is more than enough to just scoop up like 90% of the field intensity. But as you go out towards red, 800, that 2 microns is barely even scratching the surface. So this is going to be the big problem of how can we kind of make this attenuate more and get captured in our solar cell. So to quantify that, we're just going to do a bunch of electromagnetic analysis here. So one way to approach this is to imagine just a simple idealized solar cell. We make it 1 micron thick, and we assume it's created out of crystalline silicon. And we're going to put it a perfect electrical conductor, PEC, at the back contact, and forget about anything on the front. So this is a nice little idealized model that you can calculate nice closed form solutions to this and figure out how much energy will be absorbed inside of this thing as a function of the wavelength, given all the dielectric properties of crystalline silicon. So it's not like a perfect model of what happens in the real world, but it definitely builds a lot of the physical intuition of what's going on. So you run the analysis. Here's the black curve showing all the photons that are available for us. And then the red curve shows what would happen if I created a solar cell like this. So most of what's happening, you see, is this wobbling up and down. That is called Fabry-Perot resonance. So what's happening is light comes in, some of it reflects off the top, some transmits down and back again, and then you get another little transmission. There's a phase difference between those two fields. If they are out of phase, then that back and forth reflection will destructively interfere with the initial reflection, and you get kind of this weird effect where all the light wants to trap inside. And these are the peaks of the resonator here. What will also happen is sometimes that back and forth will constructively interfere with the reflection, which means you get more energy just kind of reflecting than normal. That's what these bottom little troughs here are all about. But you can then integrate all of this and figure out, okay, of the total available photons here, how many of them am I capturing? And you get about 27%. So we're going to call that the light trapping efficiency. Okay, I hit you with a bunch of photons and I capture 20% of them, and the rest just fly off back into space, never to be seen again. So step 1, let's add an anti-reflective coating, just to get rid of all that nonsense with the Fabry-Perot resonance effect. And mostly what you see is a lot of these shorter wavelengths now are being captured much more effectively. So we're assuming an idealized anti-reflective coating. In principle, this will not be absolutely perfect overall wavelengths, but it's a nice way to sort of demonstrate what will happen if we could. So you see down here these lower wavelengths where the absorption length is very, very short. There's like perfect trapping of all the photons here. And then as you get to about 550 and beyond, you see the two curves diverge. This is where the absorption length is getting very, very long, and my light trapping efficiency suddenly dies off at these longer wavelengths. So what you find now is we take the area under this solid black line, and we're up to about 40% efficiency on our light trapping, which isn't half bad. But we still have this giant void here that we'd like to recover. Because even if everything else about this solar cell were absolutely perfect, the absolute most efficiency I could ever see is 40% of a 32% efficiency. Whatever that is, something like 14% efficiency. And in principle, we got all this extra space to gather. So how can we do better? So this is where the outside of the box thinking, I guess, comes in. So the key insight is to remember, okay, I have maybe 1 micron of thickness here, but if I have, say, a giant solar cell that's printed on a giant square meter panel, I have, for all practical purposes, I have infinite length along this horizontal direction. So if I can just somehow coax those incoming photons to go that way, they'll just go on forever until they run into something and eventually be captured. So the idea is we want to somehow coax the photons into going sideways. So you notice this idea of, say, some energy comes in. If I come off at an angle, I'm traveling through a proportionately greater length than that 1 micron here, right? So if I had 1 micron down, and then if I go at like a 45-degree angle, what would you see? Something like 1.5 microns? Can't quite do that trigonometry in my head. But so it would behave as if the total distance were not, say, 1 and 1 again. It would be 1 plus 1.5. So it's as if it's thicker as if it goes sideways. So we call that a path length enhancement. That's a very popular phrase throughout the light trapping literature. So what can we do to enhance path length? Well, in principle, there's this limit called the Yablonovitch limit, and we're going to kind of derive that in a little bit. But this turns out to be about the best you could probably do in practice. And this is if you had perfect Lambertian scattering at the top and bottom surfaces here. And you would get all the way up to about 81% here and cover up all this void. So it's still not perfect 100%, but now you're getting very, very close to it, which is far more respectable. So that, we're going to derive that in a minute, but this is a common benchmark that people have strived to achieve. So this is a fun slide for me, because this is what I did a lot of my PhD research on, was how do we coax the light to scatter around inside of a solar cell. And at the time, people were coming up with all sorts of really wacky ideas that in hindsight turned out to be really hilariously bad. So one of my favorite ones was I just sort of hopped into the solar cell modeling thing one day, and this was the really hot topic, this idea of plasmonic nanoparticles and scattering light. So literally you take something like gold or silver and just sprinkle it up on your solar cell, and somehow light comes in and bounces around and magic happens. And in retrospect, it's kind of hilariously bad to do this, because you're putting all these giant particles of metal on top of your solar cell blocking light. So yeah, you've scattered some light there, but you're also reflecting more, and it's just a terrible idea. I don't know why people thought this was amazing. We have all this other wacky stuff where you're trying to do surface texturing here at the top or the bottom, and people are etching wacky pyramids and that sort of thing. But the whole idea is just how do we scatter light? This is the big light trapping craze of the early 2010s. So what we're going to do is just build some physical intuition on how to talk about this idea of light trapping. So somebody in some really obscure paper or book came up with this idea of a model N slab, which is really helpful as just sort of quantifying what it means to trap light or to enhance path length. So you imagine air, slab, air, or some back contact again or whatever, and some incident wave comes in, a little bit transmits, gets absorbed, and then falls out the other edge, and some energy might reflect out to the other side. So first thing you do is you ignore this idea of reflection here, and just pretend it goes through, it attenuates, and falls out the other edge again. So that's where the N comes from. N for no reflection, the model N slab. Very clever. So we calculate the transmission out here, and the absorption within using some basic addition. So the absorption, you notice, is 1 minus the transmission. So we're all normalized to the incident intensity of 1. And then you calculate the transmittance, and it follows this nice little exponential e to the minus alpha w. So w is the thickness here, alpha is just the attenuation coefficient, and there's kind of your 1 over e decay idea right there. So what happens then is we could, in principle, calculate the transmittance or the absorption factor here. But if I knew the absorption factor, I could, in principle, retroactively solve for the thickness of this slab. Okay? So for a 1 micron thickness, that W would be 1 micron, and I would have some attenuation and transmission. Or I could say, here is some equivalent absorption factor. Light is coming in, some of it's being absorption. I'm going to solve for that and derive, 1 micron thick. However, that same line of reasoning could technically apply for anything. So I could have some surface textured thing, and I shine light on it, and some fraction of that light gets trapped, and the rest kind of transmits or absorbs out. So I still have that absorption factor, and I'm going to solve for this quote-unquote length of this solar cell anyway. and usually I try to denote it with this L instead of a W. We call it the equivalent path length, is this idea. So all things being equal, if this was 1 micron, that would be a path length of 1 micron. But if for some reason I put something in here that caused it to absorb like twice as much energy, or say, I would say it has an equivalent path length of say 2 or 3 or 10 microns instead. That's this idea. So it's similar to the notion of like a radar cross-section, if you're familiar with that. It's just sort of this idealized reference standard to give you a rough idea of how well this thing is capturing light. So it turns out you can run those calculations on some of these simple models. For example, our little Fabry-Perot resonator, you notice it has a path length of 2 times n times w. So the 2, you notice, occurs because of the reflector at the back. So I have a 1 micron slab, some light will go down 1 micron, reflect, and go another micron. So it's as if it's like 2 microns thick. You can think of it like that. But then it also gets extended by the index of refraction, which for silicon is another factor of 3.5. So this, at the peak of the Fabry-Perot resonance, this thing will behave as if it were 7 microns thick. That's the way to imagine it. Alternatively, at the trough of the Fabry-Perot resonance, you get this 1 over n factor. So it actually behaves as if it's slightly shorter than 1 micron. So that's where you get these little troughs here. And then, of course, if I had just an antireflective coating here, it goes down and back, and the total equivalent path length is twice the thickness. Pretty simple, straightforward. So now let's talk about this whole Lambertian limit. And I have sort of a special personal place for this, because the original papers that derived this Lambertian limit, or it's also called the Yablonovitch limit, after the guy who came up with it, the arguments were really weird and convoluted. They used this obscure argument based on like the relative density of states of the incident photons inside and outside of the material, and they came up with this theoretical maximum for path length enhancement. To me, that just didn't sit right. I like to just sort of imagine, okay, let's shine light in it. We're just going to track all the rays as they go through and see if we can calculate what fraction of light is being absorbed, because that'll give us a nice firm understanding of what's happening inside this thing, as well as what assumptions are going into it in order to arrive at that result. So a fun fact, you can derive the same result. It takes a little bit longer, but I think it's a little more intuitive to think of it this way. So we start with this idea of, here is antireflective coating. Antireflective coating, you notice we put scatterers at the top and bottom. So light comes in and immediately hits this surface texture and scatters every which way. And we're ignoring any reflections from the top. So turns out this idea of Lambertian scattering is kind of the best you could do in principle for causing light to change directions. In principle, you could kind of do better, but when you average out over a large wavelength, over small texturing and whatnot, this turns out to be kind of the best you could conceivably do. So that's called a perfect Lambertian surface. So the best way to kind of imagine a Lambertian scatterer versus a non-Lambertian, which is called a specular reflection. So imagine a mirror versus, say, that white wall over there. So with a mirror, that's called specular reflection, where all the rays come in, they reflect at a perfect reflection of the incident angle. Whereas on a Lambertian surface, the rays come in and they get sort of scattered every which way. So the more, quote unquote, scattering you do, the ergodic sort of limit in that gives you this cosine theta dependence on the intensity of the light as it bounces away. Fun fact, this is also why a white object like this appears to have kind of the same brightness no matter which angle you look at it. Whereas with a specular reflector, it may not do that. That's because all the light will come in and bounce off in a very specific direction, and if you're not looking at it, you won't see that brightness. But if it's coming in and scattering every which way, you just kind of see that same brightness no matter what angle you kind of perceive the thing. So this is just kind of a weird fact of random scattering off of surfaces. So we assume this directivity profile of a 4 cosine theta. Okay, so there's a peak that goes down here at 0 degrees, and almost nothing goes horizontally in that direction. So what you do then is say, okay, all the light comes in, and now it follows this Lambertian scattering profile, and I'm just going to calculate how much energy is being absorbed in each of these little rays. So you do a flux integral in spherical coordinates, and this is the big, nasty little bugger you get here. So you notice we're going from 0 to 2 pi, so that's from vertical to the horizontal, but it's also in 3 dimensions. So we're kind of going around in azimuth as well, which is the 0 to 2 pi here. So there's our d theta and d phi. So the sine theta there is kind of our differential surface area for capturing flux in spherical coordinates. You notice I'm weighting each ray by this directivity term here. So there's more energy going that way than there is that way. Then each ray also has this equivalent absorption factor. So you notice it's 1 minus the transmission here, where it's e to the minus alpha times that length. So 1 minus t, path length, and we're just going to add all of that up to calculate total power being absorbed in that little pass. So that is a horrible, nasty integral, so we're going to apply some approximations to it. The first thing you do is you say, okay, that e to the minus alpha w secant thing is a monster. So we're going to assume that the film is very thin and has very low loss. So this alpha w term is going to be very, very tiny. How much time do we have left, by the way?
Till 1.5.
Oh, we got tons of time. Sorry. Okay. So we're going to assume this term is very, very small, and we're going to take out the Taylor series approximation on this exponential term here to get 1 minus alpha w times secant theta. And this little term here is problematic because at 90 degrees, this secant term suddenly wants to go to infinity because it's a 1 over cosine. So that's a little tricky, but we also say, well, technically, yes, there's infinite path length here, which means that approximation wouldn't work on this term at the high, steep angles. But this term here says there's almost no energy going into that ray anyway, and it doesn't matter if I'm a little wrong about it. So I'm just going to kind of brush that under the rug and keep it expressed as this. So yes, this approximation breaks down at the steep angles, but where the approximation breaks down, there's so little energy in those rays anyway that it doesn't matter, is the way you think of it. So it's a bad approximation, but the errors are not significant to the total area under that curve anyway, so who cares? So you crunch that into this integral, and you get a nice simple expression where the absorption factor is approximately 2 times alpha times w, which is effectively just the weighted average of one pass from top to bottom with an inversion scatter. Okay. So now we say, okay, all that energy now comes down and hits the bottom contact, and some fraction of that is now going to escape out of the bottom. So how do we calculate that? Fun fact, we're going to kind of put the cart before the horse here. Come over next Thursday, and we'll talk about light extraction efficiency for these sorts of things. And it turns out it's just a fraction of the area inside the escape cone to outside the escape cone. So what you can kind of intuitively say, I have this random surface here, totally randomized, and a ray is coming in, and it might kind of be in the escape cone, or it might be outside of it, and who knows. If we just sort of sample it randomly, then we get this little term here. So that means if all the energy comes in, this fraction of the energy is going to escape out of the bottom. So you do a little bit of trigonometry, and I get 1 over n squared. That. So for something like crystalline silicon, the n is 3.5. So if you square that, you get some number. 3.5 squared. Anybody know that? Somewhere around 12 or 13 maybe. Sounds right. So basically, it'd be something like 1 over 12. So we'll just average that to 1 over 10, maybe approximately. So roughly 1/10 of your energy is falling out the bottom, and then the other 9/10 is going to reflect back up for another pass. So we calculate the reflection coefficient at that little incident. So all the energy goes down and then reflects a little bit. So this represents the energy that was lost going from top to bottom. Then this is now the energy that got transmitted out of the bottom itself, and then the rest of it is the reflection that's going to come back up. So remember, we said this term is really, really tiny. So this entire little parentheses here is approximately 1 anyway. We're going to sweep that under the rug and just get this little term here. And then you repeat forever. So all those rays are bouncing back and forth, up and down forever. And eventually, they kind of either leak out the top or the bottom, or they're absorbed inside here. And you get a nice infinite geometric series, which has a nice simple solution of that. Okay? So 2 alpha n squared w. And finally, one last step, we're going to throw away that reflection out of the bottom and replace it with a perfect electrical conductor. So that 2 alpha there becomes a 4 alpha. So everything just behaves as if it's twice as thick. And you get this 4 alpha n squared w, which we then solve for the equivalent path length, or our path length enhancement. Turns out to be 4n squared times w. That is the Lambertian limit for path length enhancement. Yay! So I like that little derivation because it's very intuitive. You're just following the rays back and forth and adding up what gets absorbed and what wasn't, and it forces you to be very explicit about what your assumptions were. So if I had a very thick or highly lossy solar cell, this approximation would not work anymore, but of course we wouldn't care about it anymore because we're trapping all the light anyway. It doesn't matter. So this is a very sort of thin film, low loss approximation, and this is the absolute best path length enhancement that is possible to achieve in this particular little scenario. So fun fact, again, crystalline silicon, the index of refraction is about 3.5, so you square that times 4, and you find that the path length enhancement is about 50 times. So if you had this kind of perfect Lambertian scattering on a 1 micron thick solar cell, it would behave as if it were actually 50 microns thick. That's kind of the upshot of all that. So with that in mind, or I guess if we go back real quick, I'm getting ahead of myself real quick. So we skip back to that curve we saw here. That is where this blue curve is coming from on slide 24. Yay, right? Very exciting. So now now that we're all experts in light trapping, let's do some fun little thought experiments. So let's suppose I want to think outside the box and defeat the Yablonovitch limit, or the Lambertian limit. How can I do that? So one fun idea is to say, okay, let's just cover everything in this surface contact here with little slits, okay? And we put a big giant lens up here on top and try and concentrate all the light down into these little slits. And now they can kind of bounce back and forth forever with a very low probability of hitting one of these other slits. So it might, at first glance, seem like, hey, I've got absolutely perfect light trapping with something like this. I just need to make these slits very small and this lens very, very big. And I can beat the Yablonovitch limit, right? Get 99% light trapping efficiency, right? So I like to bring up this thought experiment because I had this epiphany once while I was working at a startup where I'd have these regular conversations with my boss, and he would just come up with all these wacky ideas. What if we try this? What if we do that? Do you think this could work? And 9 times out of 10, I always had to tell him, no, that's a bad idea, or no, that'll never work. No, that's silly. Get that out of your head. Every now and then you come up with a good idea, and we'd go for after that. And this is a nice example of something that seems like a great idea at first, but in practice, what could possibly go wrong if I tried to do this? So this is where the discussion begins, and you guys get to start exercising your engineer brains. So pretend I am the pointy-haired boss trying to say, why don't we try this? And your job is to say, is this a good idea or a bad idea? Well, why don't we? If the physics is there, it says it should work amazingly well. Okay, let me think about it for a second. Just spitball ideas. Yeah.
You have to have like perfect tracking.
Tracking is very, very important, but you're one slide ahead of me. So here, we'll just skip that. So if you're not tracking the sun is off here to the left a little bit, you're going to suddenly miss your slits and lose all your light. So that means in order for this to work, you have to track the sun. Okay. So how do you track the sun with a solar cell?
Power it.
Yeah, you get a big mechanical jiggery thing down here, and it's got all these actuators, and you have to now time it with the rotation of the Earth and track the sun. How much would that cost to do something like that? A lot. That would be expensive, and it would probably break down a lot too.
Yeah, well, if you're off just by a little bit, say your calculations are, if the slits are small enough that you go from having 100% efficiency to 0% efficiency really quick.
Yes, the sun is only like something like a half a degree in angular span in the sky, and if you're off by like 1 degree, all of a sudden your entire system breaks down. So it has to be very precise. You have all this mechanical rigging to rotate it all. So we're kind of looking at this. So you're gonna have to have these big, ugly, sort of support struts, and all this stuff is really big and heavy as well. So you're not just rotating the solar panel; you're rotating the panel plus these contraptions here on top of it, which are big and heavy and expensive. Just glass itself, in large quantities, is actually a very expensive proposition. So what do you think, like, the costs result would be to make a contraption like this. So initially I was at like $1 per watt. Now I might be at, say, $3 to $5 per watt, right? That's probably not very good. Another fun thing I like to point out is, what do I stand to gain by even doing this? Because remember, if we go back to this produced something like 85, 81% light trapping efficiency. Okay, so hypothetically, let's say that gave me a 10% efficient solar cell. And then I do this. What would I have in efficiency-wise if I did all of this perfectly?
22, isn't it? Isn't that what you're saying max was 27?
We'll go back a few slides here. So remember, so we're 81% light trapping efficiency. So the absolute best I can do is 100%. Okay? So if I had 10% efficiency with this, what would I get if that number became 100? 12%. Okay? So my dollars per watt would go from, say, $1 per watt to 80 cents per watt, all other things being equal.
The cost was way more.
Huh?
But the cost was way more.
Yeah, so that means if I do this big giant contraption, if it adds any more than 20% to the total cost, I've lost it. So your break-even point would be a 20% extra on your cost. So I got maybe 20% improvement on my efficiency, but my cost went up by like 900%. So even if it's a good idea in principle, ooh, I could get a whole extra 10 to 12% bump, but now my dollars went from 1 to 5. So that does not bode very well to do something like that. Oh, I already had the slide right here. So that was it. I'm already getting 81%. The best I could do is 100%, if that, maybe 97%. So so the expression is you're chasing pennies at the expense of dollars. So this is a great little setup in my mind for a nice light trapping. What just happened? Everything died. Did I turn this off?
The little screen on the wall just popped up a warning.
Did it?
Went red.
I only need like 30 more seconds to finish my lecture. Completely lost my train of thought. Oh, I was going to ask, remember this was all based on a 1 micron thick cell. What if I just made it 2 microns thick? Okay. That might add, 2% extra to my cost and my bottom line, but that 81 might suddenly go to 87, right? So I could marginally increase this just by making that a little thicker, say, as opposed to some big giant contraption up there. So get used to kind of thinking in these terms of what's physically possible versus what's practical versus what makes any economic sense at all. And so just because something might seem like it's a good idea, just because you can do it doesn't necessarily mean you should or that it's useful. So that's the end of the presentation. Any questions? Nothing at all? You don't get to leave until someone asks one question. Okay, fine. Thanks for coming out. That was it. So tune in next time for light extraction. All right.
Okay.
Yeah.
Let's thank James. We'll be back on Thursday. Thank you.
Yep.
Let me see.